Hi. Welcome to geometry. Yeah, we're not in calculus anymore. We're going to do geometry. Um, because if you're working with a rectangular approximation method, you might say, well, I'm not getting very good answers, but could I use geometric things in order to help me find a better area? Because there are shapes other than rectangles. So let's use shapes other than rectangles in order to find the area underneath a curve. So this problem is asking us for the area underneath that curve. A definite integral tells us the area underneath a curve. So, well, our curve is very straight this time around. So I graphed the line 8 minus 2x. There it is. And I want to figure out what the area underneath that is. So that is represented mathematically as the integral from 0 to 3. So we want to figure out what this area inside of there. Well, I know what that area inside of there is. It's a it's a right triangle and it's a rectangle. So this thing down here, oh, that's not a pen. So this thing down here, that's just a rectangle that is 3 long and it is a certain amount high. I don't know how high it is, but I bet I could figure it out. 8 minus 2 times 3 is 2. Yeah. So it's 3 long and 2 high. So that area is 6. Well, and then we've got this right triangle. We know that the height of that, or the base of that triangle is 3. And then we've got this space over here. We already established this as 2. And we know that this has got to be 8. So the height of this thing is 6. So the area of this piece is just 1/2 times 6 times 3. So that is a number. It's 9. So the area that we get is 6 plus 9. 6 plus this, which is 15. But guess what? That's what this thing is. Doop, dop, done. So that area underneath the curve is just 15. Let's get more wild. Look at this function. It's doing all kinds of things. Great. We want to figure out what the area underneath the curve is between 0 and 2. But it does do something a bit weird. So it's looking for between pen, between here and there. But there isn't really an under. Like it's all below the x-axis. So if I pictured this as a circle, let's see if I can draw a circle here. Can I make you not filled in? I'm pretty sure I can. Style, fill, none. Huzzah! Okay. So there's my little circle. All great. So that thing's a circle because it also says a semicircle, so I know it's a circle. So it's between 0 and 1. So if we found the area of that whole circle, the blue thing would be pi r squared. And so the radius of that thing is 2. But we want to cut it into 4 bits because we're only using a quarter of the circle. So that is just pi. But we still have to deal with the fact that it's kind of below. So we found areas before, and we find the areas, they were always positive. But if we go below, we should kind of do like the opposite of it. So we'll make it negative. Remember, we're doing kind of an antiderivative, which is telling us the slope. And whenever the slope was below the x-axis, we were saying that, hey, that's a negative slope. So if we're doing the antiderivative of something that's below the x-axis, then its value should be negative, just like a negative slope would be if we had a value of a derivative below the x-axis. Okay? So remember, if it's below the x-axis, it's not going to be positive. It's going to be negative. Next, we've got this one. It's between 2 and 6. So that one is above the x-axis, so we know its value is going to be positive. So that is a triangle, and a triangle is 1/2 our base, and so our base is going to be 4. Yep, so base. And then the height of our triangle is going to be 2. So that's going to equal 4. So the definite integral from 2 to 6 of f of x is just going to be 4. Neat. What about this one? So we've got our antiderivative between -4 and 2. So our integral between here, oh my gosh, and 2. Oh, that's all kinds of weird stuff. Well, boop, boop. We've got two things. It's going to be that right triangle plus whatever the semicircle ends up being. Well, we did the semicircle before. It was pi times our radius squared, which was 4. Now, we're going to use our full half of it this time. So we're going to divide that full circle in half this time. Plus, we need to get the area of that right triangle over here. So the triangle is 1/2 the area, the height, base times height. So that's 1 and then 2. Now, all of these are below the x-axis, so I want to make sure that whatever I get, I make it negative. So let's see. So that's negative. Let's see, 1/2 times 2, so that's 1 plus 2 pi. So this integral equals -1 minus 2 pi. Neat. Next one, it goes from -4 to, it's the whole thing. What? Well, we just found a big chunk of it right here. So we already did this. That was -1 minus 2 pi. And then we also did this in another example. It was 4. We did between 6 and 4. That was 4. Ah! So it'll be that plus 4. Just add them all the bits up. So that's going to be 3 minus 2 pi. Ta-da! Well, I can put it here. 3 minus 2 pi. Huzzah! And that wraps up our geometry lesson when we're doing calculus. Hooray! So make sure you've got these formulas for finding areas of shapes. And the best thing that you can remember is if you've got goofy shapes like we've been working on, you just chop them up into shapes that you can find the area of. Doesn't work with every curve, so we have other tricks up our calculus sleeves, but sometimes they'll give us graphs and we can just do geometry rather than doing any of this calculus stuff. Cool. Thanks for watching.